Okay, with this video I'm going to show how to use the Excel spreadsheet for doing the tracer analysis that's been assigned to you in assignment number 4. Problem number 2. Here's a view of the problem statement. Got a wetland mesocosm. It's used to simulate transport characteristics of a wetland. The mesocosm is a small-scale wetland. It has a length of 2.2 meters, a width of 0.79 meters, and a total depth of 1 meter. In the application, most of it's filled with soil, and the water depth in this case is 0.31 meters. The hydraulic loading rate to the mesocosm is 5.8 centimeters per day. And a pulse of lithium is injected into the inflow to the wetland. And it has the pulse has a concentration of 5.6 or 516 microgram per liter. The outflow from the mesocosm over time is given in the data file that's been posted on the website, SAV-2. The SAV stands for submerged aquatic vegetation. So this particular wetland was not a floating vegetation wetland, it was a submerged aquatic wetland. The first column in the data set is time, and the second column is tracer concentration. I've got that file. I'll show it here. Opening that file, this is what SAV-2.txt has. So the first column is time in days, and the second column says that's a mistake. It shouldn't be microgram or milligram per liter. It should be microgram per liter. So the second column is tracer concentration. It's not going to affect the results. That label there, milligram per liter, will not affect the results that we'll have. But just to be sure that it's understood that the concentration is micrograms and not milligrams. Alright, so what you're asked to do here is to determine the average flow through the mesocosm. If you know the loading rate, then you can calculate the average flow in cubic meters per day. We can determine the total mass of lithium discharged from the mesocosm while we have the tracer breakthrough at the outlet of the wetland, so we can integrate that over time and come up with the total mass. I'll show the equations to you for that. Determine a nominal residence time, which is just the volume divided by the flow rate. We determine the actual mean residence time through the mesocosm. That is what we're calling tau MOM. That's we calculate that using a moment analysis. And so we want to determine that, and we also, so tau, the MOM subscript means moment, so we're using a moment analysis as opposed to using the other procedure for calculating the mean residence time. And also using a Tankin series, or determine the Tankin series number, n, using that moment analysis. We also determine the Peclet number, the dispersion coefficient, and the dispersion number, and all those are defined in an extra document that I'll show you in a moment. We'll also, in this report, the Nash-Sutcliffe efficiency index for how well our simulated breakthrough curve fits the observed breakthrough curve. And finally, we determine the actual residence time tau and the number of tanks in series model using a method given in the spreadsheet. Spreadsheet method, and actually all these calculations, except, well, let's say for D, can be done using this spreadsheet analysis tool as well. Of course, the nominal residence time can be calculated on your calculator with no problem. Okay, so those are the things I'm asking you to do, and maybe we'll go here and look at this extra set of equations. These are straight out of Cadillac and Wallace. I think it's chapter 6 in the textbook, or in that reference book. And then it also appears in a paper by Dierberg et al. And that paper has been posted in the folder for assignment 4 on the website. So you can actually see I'll show that an image of that paper because I'm going to show the actual breakthrough curve here in a moment. Anyway, so here's the equations that are used for doing this analysis. The mass of tracer that's recovered, what flows out, is equal to the outflow rate times the concentration. The outflow rate in our case is constant with time. That's integrated over all time. So that will give us the mass of tracer that comes out of the system. The the mean residence time is calculated by taking the first moment of the detention time distribution function, and that is the f of t, which is just basically this integral of time times the discharge rate times the concentration measured at the outlet. So that's the first moment of the mean detention time, and that is defined as being the mean residence time. The variance of the residence time is just given by this equation, sigma squared. This is equation 6.31 in Cadillac and Wallace. And then a parameter called sigma theta, subscript theta squared, is just equal to sigma squared over tau squared. And then the number of tanks in series is just 1 over the theta, or the 1 divided by the sigma theta squared. To get the Peclet number, here's the equation for that. We can see the Peclet number appears in several places on the right hand side of the equation. So if we insert in here the value of sigma theta squared, we can, by trial and error, determine what the value of the Peclet number has to be in order to come up with that value of sigma theta squared. The dispersion coefficient is just the mean velocity times the length of the wetland divided by the dispersion, or divided by the Peclet number. So this gives us the dispersion coefficient. The mean velocity would just be the discharge rate divided by the width, the product of the width and the depth of the wetland, and of course the length was given. And finally, the dispersion number is just 1 over the Peclet number. So those are some equations. One of the things I didn't define here, which I have defined in class in some of the slides, what the detention time distribution function is. That's the f of t. And if you look at the set of slides that has to do with tracers in my lectures, I spent some time going through lecture on that. I define what the function f of t is and how you derive it from the tracer data. Okay. So what we'll do here is, now that I've defined the problem and shown those equations, and I also showed the tracer data, we'll come back to that. Let's look at the spreadsheet. So this is the spreadsheet that's given in the folder for assignment number 4 on the Moodle site. Number of calculations are done here. The sample data here is the one that I actually presented in class. This is from a wetland, 91 hectare wetland with a flow rate of 193,000 cubic meters per day flowing through the wetland. And here's the data. Here in column A is the time, and column B is the concentration of tracer leaving the wetland. This is probably also microgram, well, milligram per cubic meter is microgram per liter, same thing. So you've got this data, and what I provided you is the data for column A and for column B. The spreadsheet then computes the mass, integrates it so you can calculate automatically what the recovered mass is. It calculates the first moment, the second moment, all those things that are requested in the assignment. It also calculates the detention time distribution function, f of t, based on the tracer data and the time data. And then this column G is the fitted gamma function, which is referred to in the tracer, the notes from class. This G of t, which is a gamma function, this is the model that is fitted to the tracer data. well, actually to the detention time distribution function, which has the same shape as the actual data. If you look over here to the right, in doing this process, the blue diamonds are are representing the detention time distribution function derived directly from the tracer data. So this is the shape of it. The only difference between the detention time distribution function and the actual tracer data is the ordinate has a different unit. So in the tracer data, of course, the ordinate would be concentration, but in detention time distribution function, it just has units of 1/days. And you can look at the derivation of the detention time distribution function. You can find out why it has these units. But you might think of it as being kind of a normalized tracer breakthrough curve. Okay. The red line is the gamma distribution. That is the numbers that are given in column G. And that was derived by basically just changing my guess as to what the travel time distribution, mean travel time and number of tanks in series. So if I change that number, let's say for the number of tanks in series, it'll automatically change the numbers in column G. And you can see that it changes the shape of the red line. I can also change the location of it. If I change this to 15 days, you can see that it shifts a little bit. If I make it 30 days, you'll see that it shifts it a lot. So what I did was I just by trial and error tried different values of the tau and the n such that I can maximize the Nash-Sutcliffe efficiency coefficient. That's this number right here. Right now it's at 0.8288. I put 30 days in there, it's much worse. Remember, when E is equal to 1, it's a perfect fit between the data and the observed. If it's negative, then it's really bad. Even if it's 0, basically your prediction with the model is no better than what you can do just with the data itself. So what I did was by trial and error try different values of this, and I came up with 7.8 for number of tanks and 13.5 days. That gave me a Nash-Sutcliffe value of 0.902, which is quite good, and that was the maximum value that I was able to achieve. So you just play around with that. A guide for getting this tau and for n are the values that you get from the moment analysis. The moment analysis is not as good as this other fit that I just did, because the moment analysis is highly affected by the tail of the distribution. This tail down here affects greatly the actual prediction. So the calculation or optimization of the best values of tau and n are better derived by doing this trial and error procedure. Within Excel, you could actually use an optimization procedure which would automatically determine the best value of tau and n such that it maximizes the Nash-Sutcliffe value. But that would require a bit more programming, so I didn't do that. Okay, so we have our data here, and let's say we put our 2 columns of data into the spreadsheet, and what it does then is the spreadsheet is calculating for all the non-zero values that are here, and you can see that these are non-zero down to a point, and then I've just left some extra space down here in case we get a really long tracer distribution, but that's not going to be the case that you're working on. I think there's only 25 or so values that go into it, 25 rows of values. At the bottom, I summarize the numbers that are in the columns. This one had to do with the total mass, so this is the integration of the area underneath the tracer breakthrough curve, which is basically the total mass coming out. That's 510. And that's kilograms. This is, and they reported that they put about 500 kilograms in there, so that's not too bad. The second one is the first moment of the detention time distribution. That's the first moment about the mean. And or sorry, the first moment around the origin, so you can think of that as being the mean value. And then this number here, the third in column E, is the second moment. That's the variance, sigma squared. So this would be tau, or sorry, this is the first moment about the origin. It's not the value of tau. We use that in calculating tau. And then this is the second moment around the mean. And we use that in calculating sigma squared. The calculation of those these three numbers are used above to calculate these parameters. So in the spreadsheet, we just go down from where I have this graph, and I've got a section here where we do these calculations. So what you'll need to fill in here is the mean depth of flow, and that was given as 0.31 for your problem. Mean width was 0.79 meters in your case. I just put in 953 for this case. I was actually not given the dimensions of that 91 hectare wetland, so I just put in some numbers that gave me 91 hectares. The length was also not given in that case, but in our case it's 2.2 meters for this assignment. And then the mean velocity can be calculated based on the discharge divided by the product of the width and the depth of in the mesocosm. The automatically calculated is the mean residence time. It's just the ratio of the first moment divided by the mass. So that was the sum of the values in C and divided into the sum of the values from column D. For the variance, it's a ratio of the sum of the numbers in column E divided by the sum of the numbers in column C minus the value of tau squared. So that's the variance to residence time. The sigma theta squared is just the ratio of sigma squared sigma with tau squared. So then the number of tanks is just 1 divided by sigma squared. To get the Pecklin number, I put that formula in here, which uses the value of sigma squared minus 2 divided by p sub e plus 2 divided by p sub e squared multiplied times 1 minus the exponential of minus p sub e. That was that formula I said that needs to be satisfied. And so by trying different values of the Pecklin number, this number in this box right here, K64, will either be 0 or it'll be some small number. It'll be maybe a large number. So if I put in here a Pecklin number of 1, we can see that I get a negative number for that. If I put in a Pecklin number of 20, I get a positive number. And what I want to do is I want to find a value that's gets this to a minimum value. So let's say 10 to the minus 5 is close enough. That's the Pecklin number that satisfies that equation. The dispersion number was 1 over the Pecklin number, and then the dispersion coefficient was the mean velocity times the length divided by the Pecklin number. So that was done here. Okay, so those are the numbers that I'm asking for you to come up with. Now, for copying the information from this table, what I suggest you do, okay, here's our table of tracer data. I suggest that you open that file. It's a text file, which can be opened with in Excel. Let's see. This is the directory in my computer, which I've got that, but it doesn't recognize the text file, so I need to tell it that I'm looking for data with an extension of txt. If I do that, it recognizes that, and I click on that one, and it's going to come up. Let's see, I did that incorrectly. I don't want to save this, I want to open a file. So that was a mistake. Okay, so again, we just go in here. Here it is. There's our file, and the file is comma limited, so the columns are separated by a comma. So we go over here, take off the tab, put on a comma, not space, comma, and you can see that it has separated them. The title for the concentration doesn't have a comma in between, so maybe if I do that, yeah. Anyway, it doesn't matter. Finishing. This puts us into a separate spreadsheet, but here's my data then. And what we can do here is to just go down and copy this, go over to my spreadsheet, and I can carry this down like this, and I can I can paste in here the values. Okay, so now there's my numbers. I suggest here that what we do is to make sure that all these numbers are all 0. So here's the end. Line 37 was the end of the data for that, for the time data. I don't want to process anything below that, so I'm going to make this 0 and all the rest of them 0s, because this is from the previous data file, and I'm going to just make all those 0. If I don't do that, it'll kind of mess up my my result. And then I go back to the spreadsheet and I get my data from the concentration column, copy, go back to this data here, move down, and here I'm going to again paste the values, go down to the end here, put a 0 here, and then copy that and move it all the way down. Alright, so you can see here that the mass is 474, the first moment is 2501, the second moment is 22,464. You should get this. The tau value is 5.27, sigma squared, and so forth. The Peclet number still needs to be determined. You see that it doesn't satisfy this equation. You can go ahead and do that. And of course, you need to put in here the mean flow depth, the width of flow, the length of flow, and the mean velocity based on the data that I've given you for the problem. And then from that, one needs to determine by trial and error. Something's weird here. Oh, I know. This is plotting all the numbers. So we actually, to get the proper plot here, I need to end this. I've got it plotting further down. I should only plot it to row 37. And right now the plot is going all the way down to I don't know, 56 or something like that. So you need to go in here and select the data for the gamma distribution fit. And yeah, G. So I want to only go down to 37. On 37. Yeah. So that clarifies the graph. So I only go out to that far. And what you can do is you can modify this. My guide shows that the value of n was 5.27, so I'm going to put 4.5 here. And the travel time, sorry, that's not correct. The value of n is 1.4. And that the travel time is 4.7. So you can see that that's from the first moment analysis. It's not going to be exactly right. See, our Nash-Sutcliffe is only 0.66. Need to modify those a bit. Maybe if I make this 2, it greatly improves the Nash-Sutcliffe to 0.936. And you just play around with that until you can maximize it. Okay, I'm sure there'll be questions on this, but Oh yeah, one other thing here is that I decided not to ask you to reconstruct the tracer distribution curve, and that would be done with the first tab. I started working on fixing it and setting that up so you could do it, but decided that there's enough to do just determining the tank characteristics. And what I'll do is in the key solution, I'll show how that's done. Maybe I'll make another small video in which I'll demonstrate that. Okay, with that, that finishes this video.